vamos entonces a conectarnos con nuestros conferencistas de Suiza. Tenemos dos conferencias de Suiza, ellos se van a conectar al tiempo, pero son dos conferencias distintas. Esperen porque no he podido abrir acá. Entonces, tenemos primero la conferencia Mhylab, Expertise in Small, que se me mezcla el francés y el inglés, esto está en inglés. Mhylab, Expertise in Small Hydro Systematization and Hidden Hydro. Eso estaba en el programa como que lo iban a dar los señores Henri Pascal Monbelli y Vincent Denis, pero el que lo va a decir realmente es Vincent Denis. Vincent Denis está en un sitio en Suiza y Henri Pascal está con la profesora Mónica Suárez, que es la encargada de pruebas de modelo del laboratorio de la École Politécnica Federal de Lausana. Y ellos van a hablar sobre el laboratorio de hidráulica de la École Politécnica Federal de Lausana en una presentación que se llama Reduced Scale Physical Model Test o ensayos en modelo de escala reducida. Mónica había preparado la presentación en inglés, pero ella es venezolana, entonces yo le dije, pues denos la presentación en español de una vez. Entonces ella dijo que sí, que nos iba a dar la presentación en español. Yo les había dicho que estábamos un poco demorados, entonces por eso tal vez no se han conectado, pero esas son los dos conferencias que vienen ahora. La conferencia de Vincent Denis sí, él la preparó en inglés. Si alguien tiene alguna pregunta, pues pongan mucha atención y al final pues le podemos contestar las preguntas que haya necesidad. Si jamais on peut le proposer que vous pouvez commencer et après il continue avec l'autre. Je sais pas si ça marche.
Ah, pour nous c'est ok, il n'y a pas de problème.
Mais pour Vincent ça ira?
Monica, ça va?
Pour moi c'est parfait.
Oui. Alors écoute, Monica commence la présentation parce que en fait c'est...
Okay.
Moi tu sais, je suis simplement comme observateur là.
Lo que él está diciendo es que él está ahí solamente como observador. Él fue jefe de Mónica, estuvo mucho tiempo como director del laboratorio, como encargado del laboratorio y ahora se retiró. ¿Y por qué los perdimos o qué? Ah, no. Sí, entonces Henri Pascal es un experto en máquinas hidráulicas, ha hecho ensayos de máquinas de todo el mundo. Los fabricantes que están aquí en la sala les consta y han hecho ensayos en el laboratorio de la École Politécnica Federal de Lausanne. Es uno de los sitios donde se hacen la mayoría de ensayos internacionales de máquinas hidráulicas, de turbinas hidráulicas de todo tipo, y es el laboratorio más famoso. Y Henri Pascal pues era el encargado de pruebas hasta que se retiró. Ahora está colaborando como consultor independiente en diferentes proyectos y con el Mhylab, que es otro laboratorio en Suiza de pruebas de máquinas hidráulicas. Adelante, Mónica.
Ouais.
Tu peux partager ton écran si tu veux, tu peux commencer quand tu veux.
Ça marche. Alors, hop. C'est bon?
C'est bon, oui, on voit l'écran.
Okay, so sorry for all the troubles with the computer.
¿Están entendiendo? Les traduzco. Bueno.
Sorry about because I'm not able to speak Spanish, so my presentation will be in English. I hope it will be okay. So today, good morning to everybody. I also want to thank Juan Antonio Acosta for inviting me for this presentation today. It's my pleasure to give you some words about the expertise we have in small hydro fields in our laboratory in Switzerland. I will speak about systemization in small hydro, and also I will speak about hidden hydro, which is a specific topic in the field of small hydro. So briefly, a short presentation of my organization. Mhylab is a company or a foundation which is fully dedicated to small hydropower, specifically working on hydro and electromechanical equipment. It was founded more than 30 years ago, and this company, this foundation, is completely independent from any manufacturer or company. We started our activity in Switzerland, but for many years now, we are also working at international level. Mainly so far in Europe, in Africa, and with some projects also in Asia and Oceania. We do projects on river, but also on drinking water network, irrigation network, wastewater treatment plants, and so on. And we work as well for new sites, greenfield sites, as for refurbishment or enhancement of existing power plants. We have three main fields of activities. The first one is turbines, hydraulic design. We have developed hydraulic profiles for turbines in our own lab. We have a test bench where we can test many types of turbines, and we have developed hydraulic profiles and design for Kaplan Francis diagonal turbines and Pelton turbines. And so far, we have designed around 300 turbines for a cumulated output of more than 165 megawatt. And we have done these designs for around 10 turbines manufacturer mainly in Switzerland and Europe, but also some examples in Japan and New Zealand. The second activity we have is research and development, and for that we use our laboratory or hydraulic machine test bench. On this test bench we test and develop new hydraulic designs, and we perform tests for hydrodynamic and performance behavior qualification according to international standards. And the last field of activity is engineering and expertise, and we do projects. We provide technical assistance for studies, but also for troubleshooting as lenders or owners engineer. And our clients in this field are operators, project developers, international and multilateral agencies, utilities, and so on. And we also have some clients that are turbines manufacturers for which we do some specific engineering in some specific cases. So some words about the systemization in small hydro. In fact, in hydro and specifically in small hydro, we have to look for three criteria, which are simplicity. Simplicity is very important because if we have manufacturing simplicity, it means that we can provide design to small and medium enterprises active in the field of small hydro, and small and medium manufacturers that are a large part of the small hydro field. Second point, which is of course very important and not less important than for large hydro, is that we need to have guaranteed efficiency, performances, and also hydrodynamic behavior, because I think you will agree to say that if we have hydrodynamic behavior problems with small hydro, we are also in trouble, and it is not only a question for large hydro. And finally, we need to have a maximum reliability and easy maintenance, because reliability and maintenance has a direct influence on the profitability of the project. So that said, we need to find a way of meeting these criteria in small hydro. And as you know, model test is something that is expensive. And if we speak of projects with some hundreds or maybe 1 or 2 megawatt, the cost of a model test is too high to be done for that kind of project. So the solution, or one solution, is to have systemization. And what is systemization? It is a parameterization of the turbine's hydraulics. And after making this parameterization, we do model test in order to qualify the behavior and the performances as a function of the evolution of the design parameters. So it allows us then to make a custom design for each turbine in function of the exact characteristic, head and flow of the site to be equipped without having to perform again and again model test. And this helps us to meet the criteria of simplicity, reliability, and high and guaranteed performances. So regarding the research and development process, of course, this small hydro and systemization remains hydro. So we start, as we would do for large hydro, we start with CFD simulation, with preliminary design and CFD simulation, and we do numerical optimization of the profile. So you can see on this slide some example of meshes and calculation results. And once it is done, then we go, as we would do for large hydro, we go to the laboratory with the model. And I won't speak a lot about model tests, because Monica, in the next presentation, will give you more details on what they do at EPFL in Lausanne. But we make the measurement of any hydraulic characteristic of the model, cavitation, performances, and so on. So that said, up to now, with the systemization, we have developed hydraulic profiles dedicated to small hydro for Pelton, for diagonal, for axial and Kaplan turbine. Diagonal turbine is in the field of a Francis turbine. But the main advantage is that we have movable blades on the runner, and then we can comply with variable head and variable flow more easily than with the Francis turbine. And we have also some application for very low head and what we call PICO turbines, for instance, for rural electrification. So how can we apply that to hidden hydro? So what is hidden hydro? Hidden hydro is the hydropower potential that is existing in many places as non-powered dams, environmental flow outlet, all the existing water infrastructures. You have drinking water, wastewater, irrigation, you have ship locks, you have also pile-raised channels of large hydropower plants, and also you have a lot of hidden hydro in industrial processes, as desalination, for instance, cooling systems, and so on. So if we want to summarize, hidden hydro is the potential we have in any infrastructure which is presenting a discharge and a pressure or a head which is not needed for the process or for the primary goal of the infrastructure. So some examples to make it clearer. We have a potential in water network, and it is a net energy, not energy it's not really an energy production, but it's it's a net energy or electricity generation, I would say. So we have the case of wastewater turbining, where we have, for instance, on the left side of the slide, you have a town or city in altitude. You collect the wastewater, and then you bring the wastewater to a wastewater treatment plant, which is at a lower altitude. But before putting the wastewater in the wastewater treatment plant, you run a turbine and generate electricity. Another possibility is when you have a wastewater treatment plant and the city in altitude, and you release the water at a lower altitude in a water stream, river, or lake, and before releasing it, you can generate electricity thanks to a turbine. Another example of water network is everything we can find in drinking or irrigation water network. On the right side of the slide, you can see that some graphic, or where you see we have springs in altitude in the mountains, and then we bring the water from the springs to the reservoir, the main reservoir of the network, and we have a difference in altitude between the springs and the reservoir, and we can either use a pressure breaker valve or generate electricity thanks to a turbine. You need to keep a pressure breaker valve, because if the turbine is out of order, you need to be sure that you are able to bring water to the population or to the fields if it is an irrigation network. But you can also have this kind of situation between two reservoirs in two altitude levels of a distribution network, and again you can use a turbine instead of pressure reducing valve. And finally, there are also some possibilities within the network where you can replace a pressure reducing valve by a turbine and generate some electricity. Example of environmental flow and fish passes. On the left side of the slide, you have a small dam, and you need to release water for the river between the dam and the power plant, and then you can use the head of the dam to generate electricity by setting a turbine at the foot of the dam and using this environmental flow before putting it in the river. On the right side of the slide, you have a fish pass. It is an example in Switzerland where we have a quite long fish pass, and we need to attract the fishes to the entrance of the fish pass. And the flow of the fish pass is not sufficient to attract, because it's too low compared to the flow of the turbines, of the main turbines of the power plant. And then the solution was to add some flow at the outlet of the at the inlet, of the fish pass, and this additional flow is flowing through a turbine before being released, and with this additional flow, it makes water velocity sufficiently high to attract the fishes at the entrance of the fish pass. In industrial processes, this is not energy or electricity production, it's more energy recovery. And main processes where we can recover energy are in desalination plants and in cooling or heating systems. On the left side of the slide, you have an example of a unit of a desalination plant in Spain. And on the right side of the picture, you see the pump. The pump is used to generate pressure for reverse osmosis process. And after the reverse osmosis process, you have about 2/3 of the flow which consists in brine, and the brine is still with a high pressure, and it runs a turbine which is at the left of the picture. So you recover a part of the electricity you need to pump and to increase the pressure for reverse osmosis. On the left side of the slide, you see a turbine which is installed at the outlet of a cooling system of biogas thermal power plant, also in Spain, and the water for the cooling system is coming from a river. It's pumped from a river, and before going back to the river after crossing the heat exchanger, the remaining pressure is recovered by your small turbine. Two small examples on drinking and water network. The first one at the right side is a high head scheme with more than 200 meter head. And this is a power plant using drinking water and generating 1.8 gigawatt hour per year, which is not nothing. But you don't need to have a very high head, because on the right side of the slide, you see an example in Italy where an actual turbine is bypassing a pressure reducing valve, and the head is varying between 12.5 and 19.5 meter. You can have the same type of example on irrigation water turbining. Here we have an example in Switzerland with difference in altitude of 105 meter and 90 liters per second. The power is limited, 68 kilowatt, but it generates 450,000 kilowatt hour per year, which is not nothing if we consider that without this turbine, this energy would only be dissipated. One example of wastewater turbining, which is in the Swiss Alps, there is a famous ski resort, Verbier, where you have a lot of population during winter for skiing and so on, and you have a collection tank at the bottom of the village, and the wastewater, after flowing through a trash rack, goes to the wastewater treatment plant in the valley, and it is turbined before going to the treatment station, and it generates also 800,000 kilowatt hour per year, and this is working very well. We have high abrasion, but besides that, the routine maintenance is very limited, about 40 hours per year, which is not a lot for that kind of amount of electricity. We can do it easier after treatment, of course. Here, this is an example also with a head of 84 meter and 170 liters per second. It's generating 730 kilowatt hour per year, which is also very interesting for the community. And my last example before concluding, which is in Lausanne, we have a river that was flowing through the sewers of the city, which is not good, and thanks to huge infrastructures project in Lausanne, there was an opportunity to put the water in a penstock and to bring it from the top of the city to the Geneva Lake, and also going through a turbine, and it also generate electricity. So we solved two problems: the fact that we had clear water in the water sewage system, and we generate electricity, which is very good. So my conclusions: systemization first. This is a very good mean to provide hydraulic design and hydrodynamic and performance guarantee, even for very small units. It allows to make a custom design at very affordable price, which is not not bad, and also to keep things simple. And regarding hidden hydro, this is of course a field where systemization can be applied. We have wide return on experience in Switzerland, but also in other countries. The technical and economic feasibility is proven, and it's well accepted by populations and also by the authorities, which make easy the administrative process. Of course, it is sustainable, and in my opinion, it should be at least studied in any case of new infrastructure or refurbishment of old ones. So thank you very much for your attention, and I was a little bit too long, but if you have some questions, I will be happy to answer. I'm not sure I completely catch the question because the transmission was not that good. But you want to know if what has to be done besides the equipment to make a good project. Am I right?
Yes, that's right.
Okay, so of course, if you are doing a drinking or any project in existing infrastructure, what is very important is to keep in mind that the primary goal of the infrastructure is not electricity generation. So it means that besides the equipment for which you need to have or to choose reliable and good quality turbines, generator, and so on, you need to keep a bypass system, I would say, that allows to meet the goal of the primary goal of the system in which you are putting a turbine. For instance, if you put a turbine in a drinking water network, what is important is not to generate electricity, it is to bring clean water to the drinking water network for the consumers and the population. So you have to make the design in such a way that you have a bypass of the turbine that allows to provide water to the population in case the turbine is out of order, or in case you need to make an overhaul for the turbine and so on. So this is one point. Another point which is important when you try to use existing infrastructures is to consider also the waterway. And for instance, in some cases you have too many head losses in the penstock to make possible the installation of a turbine. So in that case, what is important is to make an assessment of the project. What if I need to change the penstock, for instance, to reduce the head losses and to provide characteristics that are allowing turbining? Of course, if you have a new penstock with too many head losses, it will not be profitable to change or to replace the penstock. But in case you have a penstock that is 60 years old or 40 years old, maybe the fact that you add turbining will pay for the refurbishment of the penstock. So this is really something that we have to consider case by case. But that's what I can say. I don't know if I understand, if I answered correctly the question, but
yes.
If not, please do not hesitate to.
No, yes,
to
you understand very well, and thank you very much.